So now we begin this semester by talking about three-dimensional space. So through Calculus 1 and Calculus 2, you've learned how to do limits and derivatives and integrals and applications of all, but you've been living in the 2D world. The x-axis, the y-axis, the xy plane, and you've been trying to do applications of calculus, but in the 2D world. Now, we've taken some leaps out of the 2D world from time to time. Let's say when we talk about volumes of revolution, which is a three-dimensional object. But really, we had to base everything we did in Calculus 1 and 2 off the two-dimensional world. Now we start Calculus 3, and we jump into the 3D world. Okay, in the 3D coordinate system. And so we need to spend some time first working with the 3D coordinate system in the 3D world and vector space and get comfortable with that. And then once we get comfortable with that, then we start getting into limits and derivatives and integrals and applications of all as it lives in this 3D and then the 4D space as well. Okay. So first, the 3D coordinate system. Okay, it's a rectangular coordinate system, much like the 2D space was as well. It's a rectangular coordinate system. It's the intersection of three perpendicular. We'll also say orthogonal and perpendicular. We'll talk about those terms. But they meet at a 90-degree angle. Lines with coordinate axis X, Y, and Z. They don't have to be called X, Y, and Z. You could just say first axis, second axis, third axis. We traditionally have used X, Y, and Z all throughout algebra up to this point, so we'll continue to do so. But really, it's all about, which one is the first, the second, and the third, because then we talk about the points. They intersect at the origin where all axes have a value of 0, and then we can talk about points in space and their coordinates. And so a point in space in this 3D space is an ordered triple. First coordinate of the ordered triple is from the x-axis, second coordinate of the ordered triple is from the y-axis, third is from the z-axis. And again, those are arbitrary letters, so we could just say first coordinate, second coordinate, third coordinate. But again, we traditionally would say X, Y, and Z. And then this coordinate system breaks down even further into a bunch of planes, and we could talk about octants as well. So let's talk about the planes first. So if we look at this plane here, that is comprised of the y-axis and the x-axis. That plane would be the xy plane. That's the traditional plane you've been dealing with since your days in algebra. Okay, we notice we lay that flat here. That's not always the case. This perspective of this 3D space can be changed any which way you want. It usually depends on the class. Here we'll lay the xy plane flat most of the time. Sometimes you'll see the xy plane sat up vertically. Then what we can do is look at the plane that contains the x and the z axis. So it's this plane right here. It uses the x-axis and the z-axis to make that plane. And then third, we have the yz plane here, which is comprised of the y-axis and the z-axis. Okay? And then we get our octants. Okay? So much like in 2D space where you have your x-axis and your y-axis, you have quadrant 1, quadrant 2, quadrant 3, quadrant 4. We basically have that same idea here, but we have them in octants based off of the different axes. So if we're on the positive x, the positive z, and the positive y, which would be this space that kind of sits out here, this would be considered our first octant. And then we can move ourselves around. The one that sits back here would be the second octant. The one that sits behind the z-axis back there, third, and then the fourth octant. And then we go through and do 5, 6, 7, 8 the same way. 5, 6, 7, 8 would all be below the xy plane. But you may hear something in this course where they talk about something in the first octant. The first octant means the X, the Y, and the Z are all positive. We're on the positive axes of all three, which would be the space that kind of sits out here, as if you could see this coming out. And this brings up an important idea, is that what you're viewing this video on is a flat screen, okay? A flat screen is a two-dimensional screen. And we're trying to draw three-dimensional objects in this two-dimensional space, and some of this is not done very easily. Obviously, with shading and modeling, we can try and make 3D objects appear on this two-dimensional screen, but it is not easy. And the biggest problem a lot of people have when it comes to Calculus 3 and working in the third dimension here is the visualization component of it. I do my best to try and give you some good visuals of certain things that we're working with. I don't always do the best job of that. I find it easier to do in the classroom when we're sitting in 3D space and I can model things in the space around us. But doing it on a flat screen is just like doing it on a flat board in the front of the classroom. It has its issues. So anyway, we call this a rectangular system because each point in this 3D space creates a rectangular prism. Again, so if I look at this point right here, it has an X, a Y, and a Z component to it, first, second, third. It's an ordered triple. The order matters in that, the X coordinate, the Y coordinate, the Z coordinate. So you would see, where do we match up with the X axis first? So that would be here at -2. The Y axis second, which would be here at 5. And normally you would get to this point in the XY plane if you were in 2D. But now that we have this third coordinate, we come up the Z axis, which is here, to 4, and we get this space. But if you notice, we have this unique rectangular prism here that is created through this point, and so we still have this rectangular system in play when it comes to this 3D coordinate system. So just a couple things to remember back from 2D and kind of how they relate to 3D, which is what I'm going to start this semester off by kind of showing you the things that are similar between 2D and 3D, then eventually we get to the things that are different. And so any point in 2D space creates a unique rectangle with the coordinate axis. So that's what I was talking about a second ago. And every point AB, this is an ordered pair, AB, is with a one-to-one correspondence with a point graphed in the plane. So you basically say this ordered pair then matches up with a one-to-one correspondence to a particular point on the plane. Okay? That's what we mean by that. And so, and there's not any other point on the plane that could be described with this same exact ordered pair. Same thing happens here in 3D space. So any point in 3D space creates a unique rectangular prism, again, like I just said. And then every point ABC, which is this ordered triple, is in a one-to-one correspondence with the graph point in space. When you see this, R2 and R3, they represent essentially a notation for 2D space and 3D space. We say R2 and R3 because it's based off of the number of number lines we're working with here. So if we were in 2D space, we are basically working with the conjunction of two number lines, the X number line and the Y number line, okay? And sort of the culmination of that is this is R2. If you just had a single number line, so we're looking at a number line and looking at values on that number line, that's just a real number line, okay? So we have that. R2 is using two number lines, and then R3 is three number lines, and it comes from the symbol for real numbers, which is the R, okay? And so R1, R2, R3, 1D, 2D, 3D space. But again, this point is in a one-to-one correspondence. This means once I have this ordered triple, like say -254, it has a specific location in 3D space. There's not another ordered triple that would give me that exact same location. Okay, that's the whole idea of this one-to-one correspondence. Again, some things that are very similar between 2D and 3D, the distance formula, midpoint formula, these are things that you've seen before. And so if we were in 2D space, we would only have an x and a y coordinate for our points. And if I was going to try and find the distance between point 1 and point 2, if it was in 2D space, it would look like this, okay? It would be the difference of the x's squared plus the difference of the y squared, and then I'd take the sum of that and square root the whole thing. It would give me the distance between those points. But now I have a z coordinate, okay? And so having a z coordinate just extends that out to now I have this z component as well. I have to do the difference of the z squared and add that on to this whole thing before I take the square root. Seeing these double bars here is essentially saying I'm finding a distance between point 1 and point 2. Point 1 and point 2 with a little line over it means I'm looking at the line segment. So here I have point 1 is here. Here I have point 2, which is here. There's a line segment that connects the two of them. So this is the line segment, point 1, point 2. And then if I'm finding the distance of that line segment, the notation of the double bar would tell me I'm finding that distance. And so again, the formula is really nothing new, just with a z component. Same thing happens with the midpoint formula. The midpoint formula, when you were in algebra class, would have just looked like this. You have 2 points. If they just had x and y coordinates, okay, you do the sum of the x's divided by 2, the sum of the y's. Basically, you're averaging the x's, averaging the y's. But now we have a z component to all our points, and so you also have to average the z's. And the midpoint is a point. It's this point right here that is directly in the middle so that this distance and this distance are equal distances. So that would be your midpoint, and you're trying to find that point right there with this formula. Pretty simple stuff, but noticing that there's really not a huge difference between what was happening in 2D versus 3D with these two formulas. That's not always the case. You know, when we have now a z coordinate to all our points, we don't just add a z to everything and then we're all good. We're going to start seeing some of the differences, but I show you with the very similar things first. And so if I was to find the distance between these 2 points or the midpoint between these 2 points, it would be very easy to do. So let's do distance first. Square root of, let's call this one 0.1 and call this one 0.2. It really doesn't matter. But if I did that, I would say 2 minus 5 squared and plus -1 minus -3 squared plus 6 minus 7 squared. Okay? In which case I would get the square root of what? -3 squared is 9 plus this double negative is a plus. So I get -1 plus 3, so that would be 2 squared, which is 4, plus this would be -1 squared, which is 1. And so I get the square root of 14, and that would be my distance between this point and this point. And if I wanted to find the midpoint, I'll just use MP for midpoint. It would be the average of the x's, so that would be 5 plus 2 over 2. It would be -3 plus -1 over 2, and 7 plus 6 over 2. So if I was to actually simplify that, the point that would be the midpoint would be 7 over 2. This would be what? -4 over 2. So that would be -2 if I simplified it, and then 13 over 2. So there's your midpoint. And so again, very easy stuff to do here. But noticing that when we jump to 3D, we have z coordinates now, the z variable now. In these formulas, there's not really a huge difference in jumping to that. Another thing that's very similar is the idea of a sphere. Sphere is a 3D object, but we've looked at circles in 2D space, and circle is the 2D kind of equivalent of a 3D sphere. We're going to talk more about this later on when we talk about something called quadric surfaces, but I've put it in here because it's one of those things that's very similar. If we were working with a circle, okay, and we had a center and a radius, we would say the center is, say, x1, y1, and the radius is r, and the formula would look like this. It would be x minus x1 squared plus y minus y1 squared equals r squared, okay? That would be your equation of a circle in 2D space. So we have the circle, we have the center, we have this radius, and that's a 2D circle. But now we're going to talk about a sphere. So now what we have is we don't have that circle. We dump that in 3D space, and we kind of have this sphere now in 3D space. But we still have a center, we still have a radius, but that radius extends out in all directions, 360 degrees around this way and outward here. So getting that sphere, we have the z coordinate, but the equation doesn't look a whole lot different. The center is now a 3D point, and so we have this center x1, y1, z1, and we still have this radius, and therefore we have x1 minus x minus x1 squared plus y minus y1 squared plus z minus z1 squared, where x1, y1, z1 comes from that center, and then we have r squared on the other side. And so again, fairly similar in concepts. You know, a sphere and a circle are not the same thing. You know, one's 2D, one's 3D, but the jump you can see very similar in our formula. And so if I gave you a question like this, and I said characterize this equation, and again, we'll get more into this later on in this chapter when we talk about something called quadric surfaces. We start to look at surfaces in 3D space. That's what a sphere really is. We'll get into this, but it doesn't hurt to talk about it now. And so we would have seen something like this in algebra, maybe even pre-calc, when we talked about our circles in algebra. And so you might have seen a question like this where all the z stuff was gone, but maybe a question like this that said, okay, characterize this equation, and you basically have to write it into the standard form of a circle. Well, we'll do that same thing with a sphere, in that we need completing the square to do that. And so what I'll do here is I'll group my x's, so x squared plus 8x plus y squared plus 10y plus z squared minus 6z, and I'll move the 41 over, so equals negative 41. And what I do here is I'll complete the square with the x's, the y's, and the z's. If you were doing this in algebra, you would have just done it with the x's and y's, but now we're going to do it with the x, y's, and z's. And so you should know how to do completing the square at this point. You definitely used it in Calc 2 when we were doing some integration. And so you take the linear coefficient, you divide it by 2 and square it. And so the idea here is we take x squared plus 8x, and I would need to add on 8 divided by 2 is 4, and square it. Then I go with the y's, and I say, okay, well, 10 divided by 2 is going to give me 5, and I'm going to square that and add it on there. And then with the z's, negative 6 divided by 2 would give me negative 3, and I'll square that. And so what that allows me to do here, here, and here is to factor this as a binomial. But I can't just start adding these pieces into the left side of the equation. What I need to do is also add them into the right side of the equation. So I had a negative 41. To balance it out, I'm going to add a 16, I'm going to add a 25, and I'm going to add a 9, which is basically what this, and this are. And so now what I have here is this will be written as x plus 4 squared. This will be written as y plus 5 squared. And then z minus 3 squared equals, well, negative 41 plus 16 plus 25 plus 9. That gives me what? 16 and 25 is what? 41. With the negative 41, they cancel, so I'll just get 9. And so you see right away that this now has, while this didn't, this form of that same equation has this form to it, this standard form of a sphere. In which case, if we were going to characterize this, we would say this is a sphere with a center of negative 4, negative 5, 3, and radius of 3. And remember, it's x minus x1, where x1 is the coordinate of the center, y minus y1, again, y1. It's in that minus 4. So the fact that this is x plus 4, that's really the same thing as x minus negative 4. So the x1 is negative 4, hence the negative 4 there. And also this is r squared, so r itself is 3. So anyway, if we were to characterize that equation, we can do it. But the whole point of this is that seeing that what you did back in algebra and calculus in 2 dimensions is really not that different from some of the things we're going to see in 3 dimensions. Again, that's not always the case. You don't just throw a Z on top of everything that we do, and now you're in 3 dimensions. Sometimes it's not that simple. And you'll see probably one of the most complicated things we start off with that is very different between 2D and 3D is lines. You can't just throw a Z into the equation of a 2D line and now have a 3D line. It doesn't work that way. And so we'll see that in play soon. Oftentimes, to make this transition into 3D space, it helps to talk about vectors. And that's something we're going to do a lot in the beginning here of the semester, is to talk about vectors and how we can work in 3D space using vectors. You may be familiar with vectors up to this point through other courses in physics and engineering, etc. But we will discuss vectors sort of from the ground up here, just in case you don't have as much experience with vectors when you come into this class. And so first, let's look at the definition of a vector. So a vector is a directed line segment that has 2 components, its magnitude, which is its length, and direction. And that's why we call it a directed line segment, in that the difference between a line segment is it's static. You have a point, and you could be traveling from point A to point B or point B to point A. But in a vector, you are definitely traveling in a single direction, okay? And so the length of this vector, okay, is what we call the magnitude. So that distance between P and Q in this case is the magnitude, and the direction is the direction you would be traveling. So we're going from P to Q, noted by the arrow on the end. And so there's a lot of different ways to notate a vector that have come up along the way, and we'll look at all of them. Okay, I don't particularly stick with one method of notation for vectors, because I think knowing all the different ways to denote a vector will help you moving forward as you use them in other classes beyond this course. So probably one of the most used notations for a vector is to denote it by a single letter, let's say V, and to put an arrow above that V. Sometimes you'll see it with a V with a clear arrow above it, usually a lowercase letter as well we would use to denote that vector. Sometimes you'll see the V with just the top part of the arrow like that. It doesn't really make a difference. They mean the same thing. Oftentimes you'll see a bolden letter to denote a vector. So this bolden V doesn't have the arrow above it. When you're doing it with your handwriting, it's a little bit harder to use the bolden letter, unless you really want to kind of bold it out like this. But in typeset, you would lots of times see the bolded letter to denote a vector. Another way to denote it is with the component form, which would be this here. Depending on what space we're in would depend on the number of components we have. So a 2D vector would have 2 components. First component, let's call V1. Second component we'd call V2. And we would use these triangular brackets to denote that this is a vector. Remember, when we use parentheses, we denote it as a point. So if I had a notation like this, this would be the point V1, V2. But this is the vector with these brackets, V1, V2. Sometimes, not as often, but sometimes you'll also see it with the square brackets on there as well, and the vectors can use those. The more we do this, I try and use the triangular brackets as much as possible because I think it's very clear that that is a vector notation. I don't like the square brackets as much because sometimes the square brackets could be, especially with the 2D one, could maybe look like an interval. But nonetheless, these are all different notations that we can use. And if it was a 3D vector, we would have 3 components. So we would have V1, V2, say V3 would be the 3 components of that vector, again, using triangular brackets or square brackets on the end, but never parentheses. Parentheses are only for the point. So you got to know the difference between a vector and a point. They are very different things, and the notation is very key. Another way we can look at a vector is by looking at the points that that vector travels between. And so in this case, we have P and we have Q. P is what we call the initial point. It's where we start. Q is the terminal point. It's where we end. We're going from P to Q. And what we can use here, and I should put this arrow on this here, we would do PQ with an arrow above it, and that would denote that we're working with vector PQ. Using the P and Q notation just gives you a little more specifics of what points we're working with rather than just calling it V. But you really should put the arrow above the PQ there, because if you don't put the arrow, if we just do PQ with a line above it, that's just the line segment PQ. You would want to put the arrow on that so you know it's the vector PQ. Again, all these little things make a difference. And what we would also do is look at these components a little bit closer. How did we get these components, V1, V2, V3? Well, we got it by the points that make up the vector, okay? Let's say the P is a point in n space, right? So as n component, P1, P2, P3, P4, all the way up to, say, Pn. And Q has the same amount of components, right? It's in the same space. So Q1, Q2, Q3, those are all the coordinates of the point Q. To find the components of the vector, what we would do is subtract those coordinates. So Q1 minus P1, Q2 minus P2, etc. up to Qn minus Pn. And so you always do terminal point minus initial point. And that order matters because subtraction, the order matters, and you're subtracting to get the coordinate. So this first component of vector V is found by doing Q1 minus P1, the first coordinate of the point Q minus the first coordinate of the point P. And we would continue that down the road and get all these corresponding components to our vector. Again, whether you're 2D, 3D, 4D, it depends on what points you're working with, which then would create these number of components to the vector. And it can be in any space, 2D space, 3D space, 4D space, etc. Also note that QP, okay, again, should have an arrow above it, okay? QP is different than PQ because QP would be P1 minus Q1, P2 minus Q2, up to Pn minus Qn. The order of the subtraction is different here as it is here, in which case that vector would be going from Q to P and would be going in a different direction. And so if a vector is made up of two things, the magnitude and direction, if you switch the direction, you have a different vector. Please note that every vector that has the exact same magnitude and has the exact same direction is considered to be the exact same vector. And so an example of something like that would be here. If I draw a vector here, okay, and I draw another vector over here, if the magnitude of each of these vectors was exactly the same, so that the length here to here and the length here to here were exactly the same, and if they're both pointing in the exact same direction, in fact, if these look like they're parallel, I would just assume, to tell you that, let's say they are pointing in the same direction, then this vector, say V, and this vector, say U, are considered to be the same vector, okay? What that allows us to do is we can pick a vector up and place it wherever we want and not change that vector at all, as long as the magnitude and the direction, the two things that make up that vector, as long as those two things are preserved, as long as they haven't changed, then this vector here is the same as this vector here. So whether I move this one over here or I move this one over here, they are the same vector. That can be very convenient for us when it comes to visualizing what is happening geometrically with our computation. Okay, one other thing here is there's a vector called the zero vector. The zero vector is a unique vector denoted with 0 with an arrow above it. And that vector has no magnitude and no direction. And so every component of that vector would just be 0. Okay, so something like that. That would be what we call the zero vector, say, in 3D space. All right, no magnitude, no direction. And I couldn't draw it because it doesn't have any magnitude or direction. Okay. Well, then what we need to do is we need to talk about how we find the magnitude. Well, the magnitude is essentially the distance between P and Q. And so if we look at a vector, let's say in its component form, so vector v is v1, v2, v3, vn, so those components have already been created, okay? And we wanted to find the magnitude, which we'll use the double bars, because magnitude is really a distance, okay? It's a length, so the double bars will denote magnitude. If we want to find the magnitude of v, what we're going to do is essentially use our distance formula. And we're going to do v1 squared plus v2 squared plus v3 squared all the way up to vn squared, and then take the square root of that whole thing. That'll give us the magnitude of v, the distance from the initial point to the terminal point. If we were looking at it in terms of the PQ format, okay, again, should have an arrow above this PQ, where the initial point is P1, 2, 3, etc., and the terminal point is Q, Q1, Q2, Q3, etc., and we want to find the magnitude of PQ, again, should have an arrow above it. What we would do is essentially find the distance between point P and point Q. And how do we find that? We subtract the first components and square it, subtract the second components and square it. But remember, this is exactly what V1 is, this is what V2 is, this is what Vn is, so this is really no different than this formula we have here. But nonetheless, it's our basic distance formula we've already talked about. And so that would be the distance from P to Q. Also notice that when we have P to Q, okay, and we're talking about vector PQ, and we look at the vector from Q to P, okay, and we talk about vector QP, that the magnitude of PQ is the same as the magnitude of QP. The only difference between these two vectors is their direction, okay? But the distance between P and Q has not changed depending on which direction we're traveling. Now we want to get into some basic operations with vectors. Simple ones, adding, constant multiplication, subtraction. And so let's look at two vectors. Let's look at vector v, and vector v is in the nth space, so v1, v2, vn are all the components, and u is in that same space, u1, u2 up to un. So we look at, say, adding these two vectors together. What would v plus u look like computationally? Well, computationally what you do is you just add the corresponding components together. So the first component, the second component, the nth component, and we get another vector. That's key. Not every operation yields another vector. In this case, though, we yield this sum vector, okay, where the first component of the vector is the sum of the first two components. The second component is the sum of the two second components, etc. And so that's what we would get computationally. Geometrically, what we would get is another vector, but a vector related to the first two. So here's the idea. I look at vector v and I look at vector u, and I have these two vectors here in 2D space. It's usually easier to draw this in 2D space. So it looks like it as if they're 2D vectors. Any two vectors create what we call a unique parallelogram. So what we get is if I transpose this vector up here, and I transpose this vector over here, which again, we can transpose these vectors. As long as we maintain the magnitude and direction, we can move them wherever we want. But what we get is this parallelogram. The diagonal of that parallelogram from here to here is the sum of the two vectors. So if I took vector v and I took vector u and I add them together, I get another vector, but the vector I get is this diagonal vector in this parallelogram, okay, that I create between u and v. And even if you have one vector, say, here, and the other vector is over here in, say, 2D space, remember, I can pick this vector up and I can place it so that its initial point sits at the same initial point as this other vector. So if this is vector v, I can move vector v over here so that this initial point is now here. As long as the direction that that vector is pointing and the magnitude of that vector is preserved, I can do that. So I can always move that vector to create my parallelogram, then to create my sum vector. Okay, so there's my u plus v vector. All right. What else do we have? We have constant multiples. Let's let k be what we call a scalar, a constant multiple. So if I have the scalar multiple of v and k, so I want to multiply them together, k times v, k is scalar, v a vector. What I do is I multiply each component of v by k. Again, getting a new vector, okay, but getting a vector based off of the first. Geometrically, what do I get? When I distribute that k essentially into all the components of v, I change the magnitude. So let's say here this is vector u right here, okay, and then I multiply u by k. What am I going to do is I'm going to scale that. In this case, we're assuming k in this example, in this geometric example, k is bigger than 1, which would then stretch this vector's magnitude out and now make it bigger. Notice it's still pointing in the same direction, but that big vector is now vector k times u. If k was less than 1, what it would do is it would scale my vector down smaller. Okay, so then this little vector here would be k times u if k was less than 1. But what it does is it scales that vector back and forth. And so the bigger k is, the more it's going to stretch out that vector. The smaller k is, the more it's going to shrink it down closer and closer to a magnitude of 0. But that's what a constant multiple will do. You distribute it into each one of these components. Geometrically, it scales the magnitude bigger or smaller depending on k. Okay? Also, that's thinking of k as, say, like a positive value. What if k happened to be negative? What if you have a negative times v? So something like this right here. Well, that's a constant multiple just like any constant multiple, so every component is multiplied by that negative. And what it does is it takes the vector and turns it the opposite way, thinking about changing the subtraction of p and q to now q and p, right? When you change the subtraction, you change the sign. And so all these terms have now been created as negative. And so if I look at, say, this is v here, then negative v would go the opposite direction, all right? And I can place that wherever I want. This one's placed here. Because then we talk about the difference of two vectors, right? If we do sums, then we can do constant multiples, then we can do sum and difference. Because when you add or subtract, subtraction is just a form of addition. It's adding the negative. So you can think of this as u minus v is the same thing as u plus negative v. And so since we have u, we have what negative v is, and we have addition, we can talk about subtraction. And so all that is saying, okay, well, here's v, here's u. If I want to create that parallelogram like we've done before, we know the sum is this big diagonal across that way, but what does the difference look like? Well, the idea here is that the difference would be this diagonal from here to here. Okay, that would be u minus v. It would be this cross diagonal here, where I go from the terminal point of v to the terminal point of u. That would be my subtraction, mainly because now I'm looking at this vector here, and I'm looking at this vector here, and I'm getting this diagonal of that. So whether I look at u minus v or u plus negative v, this vector and this vector are the same vector, just in different locations. They have the same magnitude. They're pointing in the same direction. And so geometrically, there's your difference vector, okay? But the idea is you add two vectors together, you get another vector. A constant multiple times a vector is another vector. The difference of two vectors is another vector. Knowing which kind of vector you get out of each one of those is important. So the computational aspect as well as the geometric aspect. There's another way to denote vectors that you may have seen before, and it's based off of this idea of a unit vector, something that we call the standard unit or standard unit basis vectors. And so first we got to talk about a unit vector. So a unit vector is a very simple concept. Unit vectors, any vector with magnitude 1 is considered a unit vector. So as long as its magnitude is 1, it's a unit vector. And we know that we can take a vector, say the vector like this, and we can scale it by multiplying it by some constant. So maybe this magnitude is not 1, but I can multiply it by some constant so I can scale it back. So now this magnitude is 1. And that would just be simply taking this larger vector and multiplying it by a constant. So if I wanted to look at the unit vector for any particular vector, if I wanted to take any vector and scale it down to become a now unit vector, I can simply do that by working with a constant multiple. And the way we do that is say, look at a given vector W. And if we look at this vector W, we can look at its unit vector. That's pointing in the same direction, right? Just scale down, let's call that V, by taking W and then dividing W by its magnitude. So if this yellow vector here was W, okay, then this blue vector down here would be the vector W divided by the magnitude of W, okay, and that would scale it to become a unit vector. We scale up or scale down depending on the original magnitude of the vector. But it's simple to take any vector and look at its corresponding unit vector by using that simple formula. Okay. Now in each space, we have what we call standard unit vectors. A standard unit vector in any space, let's say Rn, we can denote those by E1 or E2 or even En, depending on what space we're in. What happens is all the components of that vector are 0 except for one element, which is a 1. Okay? So it's a vector that's comprised of zeros and 1s, but there's only one 1 in each one of these things. And so if we looked at R2, okay, R2 has two of these, 0, 1 and 1, 0. Okay? Those are the two standard unit vectors, and if I was to draw them, they would be the vectors that sit on the x-axis and the y-axis. Okay, usually that's the direct where we could put them anywhere technically, but this would be the vector, say 1, 0, and this would be the vector 0, 1. Okay, those would be those two standard unit vectors. Okay, magnitude of 1. And the components of the vectors are zeros and ones. Only we're using 1, 1. Okay? R3 has three of them. So we have 0, 1, 0. We have 1, 0, 0. And we have 0, 0, 1. 0, 0, 1 only exists in R3 but does not exist in R2. Notice, these two, here and here, are very much the same vector. And this brings up a really important point, is that you can take a 2D vector and you can place it in 3D space. You cannot take a 3D vector and place that in 2D space. And so the idea is really pretty simple. Let's look at this 3D space here. Let's call this X, let's call this Y, let's call this Z. Okay? And so we have this XY plane that sits in 3D space, right? And so if I took this vector right here, okay, 1, 0, and I placed it on the x-axis here in 3D space, now that vector is a 3D vector. And if I took this vector and I placed it in 3D space and put it on the y-axis, now that vector is a 3D vector because it's sitting here in 3D space. Well, it's in 2D space and 3D space. How does that happen? Well, it's got to have three components here. Well, the components of this vector would be 1, 0, and 0 now for the z. Since the z coordinate is the new piece while I'm in 3D space, the z component is just 0 also, okay? And this one here would be 0, 1, 0, okay? And so a 2D vector can also live in 3D space by placing an extra 0 in that new component. So the z component, the third component, or the fourth, the fifth, the sixth component. So you can bump a vector up into higher dimensional space by throwing zeros in to all the extra new components. You cannot do the other way around. So this vector right here cannot live in 2D space because if I zero out the third component to bring it back to x and y, I do not have the same vector, right? So that's not the case there. We would label these vectors. In this case, this one here would be labeled as, let's do it in order. This one here would be labeled as I. This one here would be labeled as J. So since this one is the same, we would label this one as J, this one is I, and then this one here we would call K. Okay, and we can keep doing this in four-dimensional space, etc. All right, and so, we have these standard basis vectors. The point of this is that we can take any vector and write it as a sum of any of these standard basis vectors, right? Which gives us a new notation, which you would typically, if you've seen this before, it's this IJK notation you may be familiar with. Okay? And so let's get rid of some of this. And so we look at this example here of, say, V. Let's say V is this vector A1, A2, A3, right? This is this vector. It's got these three different components, so it's a 3D vector, A1, A2, A3. So if V equals A1, A2, A3, I can write it in other ways. I can write it as this vector plus this vector plus this vector, in which case it's vector A1, 0, 0 plus 0, A2, 0 plus 0, 0, A3. Now, that's just the sum of three vectors. So this one vector is the sum of three vectors. Well, how does that happen? Well, think about it. If I added these two together, these two vectors together, I would add their components. So the first component would give me A1. The second components added together would give me A2. The third components added together would give me 0. And then I'm going to add this third vector into that as well. So now if I add these, first two components would give me A1. Second two components would give me A2. Third two components would give me A3. And you see I get this vector A1, A2, A3. So yes, I can break this vector here down into these three vectors added together. All right, now I'm going to go one step further. I can take this first vector, A1, 0, 0, and I can write it like this. A1 times 1, 0, 0. Right? A1 times 1, 0, 0. Now that's just a constant multiple times a vector. How does that work? This has to be multiplied in here, here, and here. And so what happens is A1 times 1 would give me A1, then 0, then 0. So this is the same as this. And I do that sequentially. So A2 times 0, 1, 0. A3 times 0, 0, 1. But remember, 1, 0, 0 is I. 0, 1, 0 is J. And 0, 0, 1 is K. It's those standard unit vectors. And so what I can then do is say it's A1 times I plus A2 times J plus A3 times K. And so another way to denote the vector A1, A2, A3 is in this IJK notation, which would be A1 times I plus A2 times J plus A3 times K. You see these either with boldened IJKs, okay? When you see it in type form, you'll see that. In handwriting, it's a little hard, so what you'll see lots of times is they'll put little carets above the IJK to denote that those are your standard basis vectors. But either way, this and this mean the exact same thing. So if I was going to express, say, some vectors in that format and do some computation, it should be very easy to do. This is used lots of times because this is very similar to, say, basic algebra polynomial computation. So let's say A is J, right? So A is, 2J. So you could also write that as 0I plus 2J plus 0K if you really wanted to do the I and the K components. And let's say B is 4I plus 7K. So let's say 0J plus 7K. And I wanted to do this computation of 2A plus 3B. Okay? So 2 times vector A plus 3 times vector B, and I want to do this all in this IJK format. Well, this is really nice to do it in this format because it's a lot like polynomial computation. So 2A would be 2I plus 4J plus, It would be 0I still plus 4J plus 0K. And 3B would be, 12I plus 0J plus 21K. Okay? And then if I were to add this and this, well, I add their components, right? When you add two vectors, you add their components. So you add your I components, which is your first components, your J components, and your K components, which is a lot like adding like terms in algebra, in which case now I have 12I plus 4J plus 21K. And so it can make some of your computation maybe look easier because it's related to something you've done, But nonetheless, you should be able to go between component notation, which is this A, B1, A2, A3, standard unit notation, which is the IJK notation, and realize that they all mean the same thing. But we do this by looking at what we call these standard unit vectors. Okay, I, J, K, which are the three-dimensional standard unit vectors. And again, they kind of sit on the corresponding axes. So we have, here's the x-axis, so that would be my I. Here's the y-axis, so that would be my J. And here is the z-axis, so that would be my K. But remember, we can pick these up and put them wherever we want. And the reason why it's easier to put them on the axis is because the origin is 0, 0, 0. And the ending point here, we could say, is 0 for the x, 0 for the y, and 1 for the z. And then if I looked at that and I said, okay, let's do terminal, which is here, minus initial, which is here. 0 minus 0 would give me 0. 0 minus 0 would give me 0, and 1 minus 0 would give you 1, and you see that's the k vector. So placing it on the axis makes it easiest for us to look at the components as well as the points and see how they all match up.